Hey, so welcome back. So we finished chapter 1. So if we go back and look at chapter 1 of the differential equations class, you will see that we talked about, say, just definitions. It was a section 1.1, and section 1.2 also contained definitions. And so these were things like what are differential equations, what are linear differential equations, what are solutions to differential equations, initial value problems, etc. There's a little bit in there about when a differential equation's initial value problem is actually solvable, and that required that the function be continuous and the derivative of the function with respect to the dependent variable also needs to be continuous within a region of within a region of the initial value. So what do we do now? Oh yeah, we did talk about a few other things, right? We did Picard iteration, we did slope fields, and we did Euler's method, right? So those are all qualitative and some quantitative ways of approaching a differential equation where you don't know how to manually, or what we call analytically, solve the differential equation. So the goal is to find what engineers call analytic solutions to differential equations. This differs from what mathematicians would call analytic, which would be like something that can be represented as a power series. But in general, we're looking for some sort of closed form solution to the differential equation, and that's what mathematicians would say. So if you look at it, we are going to be looking at, say, maybe two main methods for doing this by hand in chapter 2. One of them is going to be separation of variables, and separation of variables basically means that the differential equation can be written as a product of two functions, one that's a function of the independent variable and one that is a function of the dependent variable. And when you do this, you can actually just divide by the function of the dependent variable and multiply over by, say, dx, in sort of a heuristic way of talking about it. Really what we're invoking is the chain rule. And when you do this, you can just integrate both sides like you normally would. So what this is going to bring up are a lot of techniques that came from Calculus 2. So you're going to be able to do U substitution. You're going to need to be able to do, say, trigonometric substitution. That's going to come up less often. But what's really going to come up a lot in this class is integration by parts. And so make sure you go and review those methods. And if I have time, I'll try to do a quick video just reviewing all those, but time is constrained. And so if you go back through those basic methods, then we can, then you should have no issues dealing with separation of variables. So go ahead and give that a try, and we'll talk about that in this lecture. The next lecture that we're going to talk about is going to go over another technique called where we're going to be multiplying by what's called an integration factor, and this is for linear differential equations of the first order, and that's going to invoke the product rule. Just like the separation of variables is using chain rule, now this next one's going to use the product rule. Basically, any technique that we see in calculus or differential equations that we can actually do any sort of real solving is almost always going to be some sort of combination of chain rules and product rules that we're trying to play with or do anything with. For instance, if you think about integration by parts, integration by parts really comes from integrating the product rule and then just rearranging things, and that becomes a technique. But it's just product rule at the end of the day. U substitution, it comes from chain rule, and now the separation of variables also comes from chain rule. And so a lot of these techniques that we're doing really are just invoking a little bit of Calculus 1. It's not that complicated, and just go back and make sure you remember how to integrate, and you should be fine. Okay, so I don't really have anything extra to say. Oh wait, this is me. I have plenty to say on this. So one thing that's really cool about separation of variables is that you can actually use this for partial differential equations. And this is the main tool for solving partial differential equations. And if you can't separate variables in partial differential equations, then you're pretty hosed. You can't do anything. So what's neat there, though, is that instead of just being a separation of variables between dependent and independent variables, for a partial differential equation, you actually have multiple independent variables, and then you want to be able to separate those. what that ultimately leads to is a collection of ordinary differential equations that arise from solving this PDE. I'm not going to ask you to do that, don't worry. If you start getting scared about me talking about multiple independent variables and PDEs, no worries. And this class is just an ODE class. But I think it's fun to mention. And what's really cool is that it's actually the principal tool that comes up in solving quantum mechanical problems with the Schrodinger equation. So basically, you can take the Schrodinger equation that is, say, time dependent, and what you can do, because maybe I should say something. So solutions to the Schrodinger equation are basically distributions that evolve in time. This is because you can't sort of localize a point at any. You can't localize a small particle at any particular point, but you can give it a sort of a distribution of where it should be. And so that distribution changes with time, and what you can do then is you can actually separate out say the position, the x variable from the time variable, and turn those into two different ordinary differential equations. And then after that, there's a whole theory that goes behind solving each of those. The time one is usually pretty straightforward. It just becomes e to the I t or whatever. But the position one invokes all sorts of really high level calculus. So yeah, maybe we'll talk about it sometime. But for now, we'll leave that alone. Okay, so yeah, anyway, so what are we actually doing is we're just going to be doing some separation of variables, taking this product, dividing by 1, multiplying by dt, and integrate. That is this whole method, and there is really nothing else to it. Yeah, there's some really cool applications out there. You don't have to know them, but I think they're good to know about. In any case, let's go ahead and jump into it, and yeah, let's have some fun.
Okay, so today we're going to talk about separable differential equations. All right, and these are basically ODEs that you can write like this. So you're going to have an equation dy dx is equal to, say, p of x times g of y. And if you're following in the book, this is section 2.2 in Nagle, Saff, and Snider's book, Fundamentals of Differential Equations. And 9th edition, if you're keeping track. So these are special differential equations, and basically you can actually separate the equation into two different integrals. So for instance, if we go ahead and write it like this, then we get, say, dy over dx. Heuristically, we get this. So dy over g of y, and we get p of x times dx, and then you integrate both sides. You come out with an integration constant, and that's basically it. Though technically it's a little bit more complicated, and it uses the chain rule, or U substitution if you want. And so basically, more formally, what we get is we write this as, say, 1 over g of y times dy dx is equal to the integral of, say, p of x, and then we take this integral with respect to x. And so then here, this cancels, and it gives us, well, basically that. So basically, U substitution would be, would give us this. So, but never fear, you're never really going to have to worry about that little technicality. What you're going to do is you're going to have to just learn how to, remember how to integrate a lot of things. So one of the examples that they give in the book is they give this one, where it's dy over dx is equal to 2x plus xy divided by y squared plus 1. Now, this is actually not too bad to integrate, but first we need to separate the variables. So I'm going to pull out an x out of the numerator, and what it's going to leave us with is 2 plus y over y squared plus 1. All right, Now I can divide by this, and I can multiply by dx, and that gives us something else. So it gives us dy times y squared plus 1 over 2 plus y is equal to x dx. Okay. Now it's just a matter of figuring out how to actually integrate this. So it shouldn't be too bad. And this one's a little annoying because it actually has a quadratic over, it's not a simplified fraction. So in this case, we'd actually have to use sort of long division. And let's see, what can I do? So something you could do in order to solve this one really quickly. If we want to simplify this, not to make a complicated example right from the beginning, we have y squared plus 1 over 2 plus y. And if I say add, say 2y and subtract 2y plus 1, I think this should work out, over 2 plus y. Then what is that going to give me? It is going to give me, so we're going to have two different equations. We're going to have y times y plus 2 here, minus 2y plus 1 divided by 2 plus y, and say divide this by 2 plus y. And then this will end up canceling here and here. And so what that ends up giving us is it gives us y minus 2y plus 1 over 2 plus y. All right, so that's a little bit nicer. And we can make it even nicer if I do sort of the same trick again. And I write this as y minus 2y, say plus 4 minus 4. And so if I subtract 4, it's just going to give me minus 3 here over 2 plus y. And so same game again. So we have y minus, say it's going to be 2 times y plus 2 minus 3 divided by y plus 2 divided by y plus 2. And ultimately what we get is we have y minus 2 minus 3 over y plus 2. Okay. So avoiding doing long division, this is sort of a neat little trick that you can do to simplify your equation. So what we get then is on the left-hand side here, we have y minus 2 minus 3 over y plus 2 times dy is equal to x dx. And now we can integrate both sides. If I integrate both sides, on the left-hand side, I get y squared minus 2y minus 3 times the natural log of y plus 2 in absolute values, but we'll neglect that for a minute, is equal to x squared over 2 plus c. So we're integrating with respect to dx on the right, and we're integrating with respect to dy on the left. And let's see, what else do we get? So we're not really going to be able to solve this in any nice way. So we actually have to end up stopping here. The big reason why is because we have a y on the outside and a y on the inside. And so this is actually going to be our solution. And so this is what we'll call an implicit solution to the differential equation. Okay. So that might be a little scary of an introduction. Honestly, they're usually not this hard. In fact, if you even look at the book, they even bother resolving this particular question. But it's not impossible to do if you're sharp with your polynomial and rational functions. What we can do is, let's go take a look at what they actually write down as example 1. So if we take a look at this one, so it's going to be example 2 for us. We're going to have, say, dy over dx is equal to x minus 5 over y squared. Now this one is going to be trivial, so I won't even need a whole page for this particular example. So what this gives us is, it gives us, if we sort of separate the variables, we get y squared times dy is equal to x minus 5 times dx. Now, this we can integrate, nice and easy. So put little integration bars on each side. And so you end up getting y cubed over 3 on the left is equal to x minus 5, x squared minus 5x here on the right. But remember plus c. Now we don't need to have a plus c on both sides. The constant is arbitrary, so I could put another plus c here, and then I could just subtract it over, and then you get sort of a plus c twiddle. So just to keep things from getting too complicated and having too many arbitrary constants floating around, they all can be accumulated into just the one on the one side. So we'll just leave it like that. Now this one is actually one we can solve. This isn't too bad. So if I multiply by 3 and I take the cubed root, we're done. And so we get y is equal to, say, x squared minus 5x plus c divided by 3, and we have the cubed root, right? And so that's probably a more typical problem that you're going to see. It's not too complicated to do these. Sometimes you might have to use integration by parts or something like that, but yeah, I wouldn't worry too much. Okay, so now the next one is asking us to solve the initial value problem. And so let's go ahead and take a look. So they give us dy over dx is equal to y minus 1 over x plus 3. And they're telling us that y of negative 1 is equal to 0. So we're not starting at 0 for our x naught, we're starting at negative 1, but that's fine. Okay, so again, this ends up being kind of straightforward. So we have y minus 1, and we're going to divide it over here. And we have this x plus 3 here, and we're going to leave it there. So what this gives us is it gives us dy over y minus 1 is equal to dx over x plus 3. Now if I go ahead and integrate both sides, on the left-hand side I get natural log of y minus 1, and on the right-hand side, and let's keep these absolute values, I mean they do kind of matter, is equal to the natural log of x plus 3, and we'll just keep one integration constant. Okay, so now we're kind of left here with trying to decide if we should have something in absolute values. First of all, we can get rid of these natural logs. That's something we can do pretty quick. So I can exponentiate both sides, and that's going to leave me with y minus 1 here in absolute values. And then over here, if I exponentiate this, it can be turned into a product of two exponentials by splitting over the sum. And so that's going to give me e to the c times x plus 3. Okay, so now we need to figure out if we want to keep these absolute values, and it's really going to come down to our initial point. So yeah, so basically what we're going to have, I really want to get rid of this absolute value because, I mean, I'd like to be able to solve everything in terms of y. Let's go ahead and on to the next page. So we know, for instance, one point we know is that y of negative 1 is equal to 0. And we have that y minus 1 is equal to, say, e to the c times x plus 3. Okay, well, let's see. Okay, so we have the absolute values, and we really want to get rid of them. So what I'm going to do is I'm going to keep in mind that absolute value of y minus 1 is equal to, say, plus or minus of y minus 1, and absolute value of x plus 3 is equal to, say, plus or minus absolute value plus or minus x plus 3. So what I can do then is I can write this as y minus 1 is equal to, say, plus or minus e to the c times x plus 3. So the only things that we're wondering about is if this whole thing is going to be positive or negative. If I had, say, a positive and negative over here, I can move it over there, and then there's going to be another positive and negative over here, and that's moving over here, and some combination of them is going to be positive or negative. So I'll just write it like that. And then that tells me then y is equal to 1 plus or minus e to the c times x plus 3. Now, if I go ahead and I replace, say, this guy by another constant, say y is equal to 1 plus c twiddle of x plus 3, then it just comes down to finding the c that would give us their initial value. Our initial value of being y of negative 1 is equal to 0. So I'm looking for, say, something that satisfies 0 for y. This is going to say our y naught, and this is our x naught. And so is equal to 1 plus c twiddle times x naught, and x naught here is negative 1 plus 2. So now that gives us the ability to solve for c. And so c is then going to be negative 1 divided by, plus 3. So this is altogether going to be 2, and so I'll just divide by that. So 2 is equal to c tilde. Right, so there we go. That tells us then that y is equal to 1 minus 1/2 of x plus 3. And that's the solution. And if you want, you can go into the book and you will see that we're in agreement here. Okay. So that's fun. So let's go take a look at yet another example. So here, this example is, say, dy over dx is equal to 6 times x to the 5th minus 2x plus 1 divided by cosine of y plus e to the y. Okay, so if I take a look at this, I can see that the numerator here just involves x, the denominator here only involves y, so I can just multiply over this denominator over here, and I can multiply dx over there, and then I can just integrate. So here I'm going to get cosine of y plus ey, and this times dy, is equal to 6x to the 5th minus 2x plus 1, and this times dx. And integrate both sides, and what are we going to get? Well, on the left-hand side, the integral of cosine is just sine of y, and integral of e to the y is, again, e to the y. And this is equal to, say, 6 times x to the 5th. Well, x to the 5th becomes x to the 6 over 6 when you integrate, and then that is going to kill the 6 there, so we get x to the 6 minus negative 2x squared over 2, so that's just going to be x squared, and plus x, and then, of course, plus c. Right? Now you can ask, all right, well, how do I solve for y? Well, there's really no hope. We have a sine of y here, and we have e to the y here. We'd want to take arc sine of both sides to solve for that here, but we'd also have to take natural log to solve for this one, so sort of conflict with each other. Truth is, there's really no nice way of getting at this, and so we'll just have to stop there. And so we're going to consider this an implicit solution. Implicit. Oh my god, I can't spell. Implicit solution. Solution. Yeah, okay, I did spell it right. Right, so this is our implicit solution to the differential equation. Right there. Okay, that's nice. Okay. Yeah, so this is actually a really straightforward method. We've actually talked about it a few times in the other lectures. What's going to come down to is how well you remember to do things like integration by parts, and how well you remember how to do just your general integration techniques. We had one tricky one back at the beginning here, and I could have jumped from this one, did long division, and etc. And you know what? Why don't I just show you how to do polynomial long division? I'll just throw it as a bonus here at the end. Yay, bonus lecture. So y squared plus 1 divided by, say, y plus 2, and we want to figure out how to get what I had without doing those tricky stuff that I did before. So what I did before is I added and subtracted 2y in here, and that's because I want to be able to factor out the y squared, and then I had another term that I need to do that again. And guess what? That was just me doing the long division, just sort of off the cuff. But let's do this sort of properly. So let's see. So we're going to have y squared. Remember we had a 0y here, and then plus 1. And I'm going to have this term y plus 2. Now, in polynomial long division, you start at, say, you have 1, 2 terms, so you're going to start here. And then you just sort of match the leading term. So here my leading term is y, the thing I'm dividing by, and here it's y squared. So I need to multiply by y. So if I multiply this by y, it gives me y squared plus 2y. And if I subtract, then I'm going to get minus 2y out of it. All right? Then we drop this down, right? And so we get plus 1. And now again, I'm going to match my leading term. And so that tells me then that I need to multiply this guy by negative 2. So I'm going to put minus 2. And what's that going to give me? Well, I get minus 2y plus 4. And I'm going to subtract that. And so that gives me 1 minus 3. And there we go. Now since I'm here, and I've run out of sort of spots to put things, I say we have a remainder of minus 3. And so then I can rewrite y squared plus 1 as this guy times this guy plus a remainder term. And so this is equal to y minus 2 times y plus 2, and then minus 3. Now if I divide this by y plus 2, so I get y squared plus 1 divided by y plus 2, then what do I get? Well, I'm going to divide this by y plus 2 and divide this by y plus 2. And that first term, you get something that cancels. So you get y minus 2. You get minus 3 over y plus 2. Okay, well, there we go. That's what we get. And if you look all at the beginning, oops, too far. What do we get? So we had a y minus 2 and then minus 3 over y plus 2. So it was exactly what I did just by sort of winging it. So, okay, so there we go. Other things that are going to come up in here and sort of something that's kind of more remedial. Let's talk for a second about integration by parts. We have some extra space in here, and so might as well do it. So let's talk about a problem that you'll run into, say, for integration by parts. And yeah, let's see. So let's say, I think there's an exercise in the book. Let me see if I can pick that out. Yeah, there we go. So this is exercise number 9. I really like this one, partly because it forces you to do some good old integration by parts. But let's see. So we have dx over dt is equal to t over x times e to the t plus 2x. All right, and you might immediately object and say, wait, I don't have this written as g of x times p of y, or whatever symbols I used before. I have this guy. It has both of them inside of it. That doesn't work. But what we remember is that we can actually rewrite this as t divided by x, and then we have 1 over e to the t times e to the 2x. We can split it over the sum. And so I can move this guy over here, and I can move this guy over here, and what do we get? Well, what we get is we have t over e to the t times 1 over x e to the 2x. All right, so now I can multiply this denominator over, and I can multiply dt over, and so what this leads to is it leads to x times e to the 2x times dx is equal to t times dt, times, oops, e to the minus t dt. All right, so I can integrate both sides. And now I need to use integration by parts. So what is integration by parts? Let's put this in a different color. So integration by parts is integral of u dv is equal to uv minus the integral of v du. This is something we get out of the product rule. And so if you basically take the product rule formula and you integrate both sides and you move some things around, this is exactly what you get. But now we use this as a technique for integration. So why don't we go ahead and do it? So in blue, I'll go ahead and do this guy. So we get the integral of x times e to the 2x dx. And the idea is you need to select a u. So I'm going to select u is equal to x. And the reason why is because I know when I take du, I'm just going to get dx. And so the function sort of vanishes when I do that. On the other hand, if I take dv is equal to e to the 2x, well, e to the 2x is pretty easy to integrate, so that's one reason why I chose it. And if I keep iterating dv's, or if I integrate dv, it sort of sticks around, which isn't the best. If I chose dv to be this, then I would have gone x squared over 2, and that wouldn't help me at all. And so choosing dv is equal to this is done because partly this integral is easy to do, and on the other hand, using this as du, a term disappears. So we get e to the 2x over 2, and that's by chain rule. All right, so now let's put it together. So I get x times e to the 2x over 2, so that's u times v, minus the integral of v du. So v had a 1/2 here, so I'm going to pull that out. And then we have e to the 2x, that's coming from the v as well. Now I'm going to write this as du here, but du is just dx. Okay, now I can go ahead and finish integrating that, and that gives me x times e to the 2x over 2 minus 1/2 times e to the 2x over 2 again. And so we get x times e to the 2x over 2 minus e to the 2x over 4. Okay, now in green, let's go ahead and do the other one. So same deal. We get the integral of t e to the minus t, and this is going to give me setting u is equal to t, I get du is equal to dt, and setting dv is equal to e to the minus t, I get v is equal to minus e to the minus t, right? That's now putting those together, I get u times v, so that's t times e to the minus t, and then we get a minus sign popping out, minus the integral of v du. So du again was just dt, and v is minus e to the negative t, and I'm going to use that minus sign to flip the sign there. Okay, so now I get minus t e to the minus t, and I can integrate this, no problem, and it's minus e to the minus t. We had a minus sign pop out by chain rule. And ultimately, this is the term that's going to end up getting c. So let's take a look at the answers we get. Let's do this in red. So the answer we get is x times e to the 2x over 2 minus e to the 2x over 4. And so I'm continuing this equation here. So on the left-hand side, that's what we get. And on the right-hand side, what do we get is we have minus t e to the minus t minus e to the minus t plus c. Now again, there's nothing we can do to solve anything in here. X is both inside and outside of an exponential, so there's really no helping it. But yeah, so again, this is yet another implicit solution. But yeah, that's the solution to the differential equation. And I guess, yeah, so that was a review of integration by parts. Things I could change is, say, for instance, I had like an x squared here, then you'd basically have to do this whole process over again, because you'd get, instead of a du being dx, you'd get du would be 2x dx, and then you'd have to do the whole process over again. But you could just iterate this until all your polynomials vanish. So yeah, but anyway, yeah, that's not too bad. Okay, so I hope this was instructive and you get a general idea of what's going on. I mean, all the time we just basically have two terms, one that maybe we can multiply or divide over, and another one that we just leave, but we take dx and we move it to the other side, and then we just integrate. And so, and then after we integrate, we just have to look back at calculus 2 to see how we do it. And so this could involve things like integration by parts, use substitutions. It could use lookup tables if you need to. but the methods are basically what you should know already. And if you don't know, just send me an email, and I'll be happy to answer it. And if you're from the outside world, comment in the video description, and I'll help you out there. In any case, I hope this was helpful, and we'll cut back to my outro.
Okay, welcome back. All right, so that was separation of variables. And so really all it came down to was writing the differential equation as a product of functions of the independent and dependent variables. And then it's just moving things around and integrating. There really isn't too much to that. Just make sure you go back and you review things like integration with parts, and use substitution and all those good integration techniques that came straight out of Calculus 2. So, maybe this is a bit of a boring lecture today, but I don't have anything fancy to show you, but I just need to make sure I recorded this outro while I had the opportunity. And so then next lecture we'll get into this whole integrating factors and linear differential equations of first order. And and those are going to be the two main techniques that we're going to look at here in this class. And I'll see if I can wiggle in something else, but we want to get to chapter 3 to talk about some applications, and then into chapter 4 to go into sort of second order linear differential equations that are actually used all over physics and engineering. Okay, I'm gonna go, and thank you.